This is part 4 of the chapter 12 lecture notes. Um, we were on this slide, I believe, when the last one ended, and I was telling you that Punnett square problems are probability problems. So Punnett square problems are not the only way to solve um, genetics type problems. So let's talk about probability in mathematical terms. So probability is given as a fraction or decimal equivalent, or it can also be a percent. So probability of 0 means that the event will not happen, and a probability of 1 means an event will happen. So it is certain. It's like 100%. 0 is like 0%, and 1 is like 100%. So anything that is chance ranges between those values. So the chance of flipping a coin and it landing with heads up is 1/2, or 0.5, or 50%. Okay? So if we look at probabilities in terms of rolling a die, all right, so the chance of rolling exactly a 5 is 1 out of 6. The chance of rolling exactly a 4 is 1 out of 6. So if you want to know what the chance is of rolling a 5 on the first die and then a 4 on the second, then you would multiply. This is called the product rule. So you would say 1/6 times 1/6, which is 1 over 36. And when I do my math, let me try not to screw up the writing. Okay, so 1/6 times 1/6 equals, you multiply the top two numbers, 1 times 1 is 1, and the bottom two numbers, 6 times 6 is 36. So that's a 1 out of 36 chance that you would roll a 5 and then a 4. Okay, and then when there's multiple ways or tries for a chance outcome to occur, the overall probability is the sum of the individual events. So if we're still looking at examples with dice, if you can win by rolling a 4 or a 5 with one die, then the overall chance of winning, the chance of rolling a 4 is 1 out of 6, the chance of rolling a 5 is 1 out of 6. Now, this is not saying that you're going to roll a 4 and then a 5. It's saying that you can win by rolling a 4 or a 5. So you're going to roll the dice one time, and what is your chance of rolling a 4 or a 5? Now, you can do this in your head because you know that there's a 4 and a 5, and then there's 4 other numbers. So that's 2 out of 6, or 1/3. But you can also just add up. This is the sum rule of probability. You can add up the 1/6 plus the 1/6. And when I do those types of problems, I'm old school, I put them like that. Oh, crap, I didn't mean to do that. Um, okay, and then, okay, so then you add the top two numbers, the numerators. So 1 plus 1 is 2, and so that's going to be 2 out of 6. And then you reduce that. 2 divided by 2 is 1, and 6 divided by 2 is 3. So you have 1/3 of a chance of rolling a 4 or a 5. That's the sum rule of probability. And then you can combine the laws of probability, or the probability rules, for complex random events. So the chance of rolling a 5 and a 4 in any order is: the chance of a 5 first is 1/6. The chance of a 4 second is 1/6. So it's 1/36 chance that you're going to roll a 5 first and a 4 second. But if order doesn't matter, we might also roll a 4 first and a 5 second, which again is 1 out of 36. It's just, you're just changing the order of the numbers. So then if we want to know the chance of rolling a 5 and then a 4, plus the chance of rolling a 4 and then a 5. Now we're going to incorporate the sum rule, which is 136 plus 136, which is 236, which equals 1 out of 18. Now, I do not normally go over probability this much in genetics, because if you go back to a Punnett square, um, let's just do this one. Okay, so in the Punnett square on the left, which has already been done for you, what is the chance or the probability that the offspring are going to be big P, little p? Well, it's 100%. You can either represent that as a 1, or you can represent that as, um, uh, I guess you could say, well, definitely 100%, or, I mean, you could say 4 over 4, 4 out of 4 if you did it as a fraction. Okay, so let's look at the second Punnett square, the one on the right. And if we fill it in, one offspring can be big P, big P. You can have two possibilities that are big P, little p. So what this is telling you is that there is a 1/4 chance that the offspring will be big P, and you can also represent that as 25%. There is a 1/2 chance that the offspring will be big P, little p, and you can also represent that as 50%. And then there is another, again, a 1/4 chance that the offspring will be little p, and you can represent that as 25%. So, so that's how we use probability. We just use the Punnett squares because using a Punnett square helps you to visually, very easily determine all the possible combinations if you know the parent's genotypes. Now, we're going to talk about pedigrees, and a pedigree is like a family tree, but we're using it for a different purpose. We are using it to show um, the a particular trait in a family. So in a pedigree, a male is a square and a female is a circle. If the male is affected with the trait that we're looking at, that we're studying, then we shade in his square. An affected female is a shaded circle. When we don't know the gender, this one's new to me actually. I've never used gender unknown, but that's a diamond shape. And then if the male is deceased or the female is deceased, we put a diagonal line through. And if you have an affected female who is deceased, you put a diagonal line through it. So when we look at this pedigree, we have 3 generations. We have generation 1 on the top line, generation 2, and then generation 3. So in generation 1, we see that there is you can't say husband and wife because you don't know that they're married, but you see that there is an affected male, and then there is an unaffected female who have 3 children together. One is an unaffected male, another is an affected female, and the other is gender unknown. The unaffected male son marries or has children with an unaffected female, and then they proceed to have twins, female identical twins, who are unaffected. Now, this is a pedigree analysis for alkaptonuria, which I will have to look up for you. First time I've heard of that disorder. So the shaded individuals are blue, they're affected, and then if they're unaffected, they are yellow. And what we know about alkaptonuria is that it is a recessive disorder. It is what we call an autosomal recessive disorder. So that means you have to get 2 little a's to be affected with alkaptonuria. You have to get one little a from each parent. So here's what we can tell in the first generation. The first generation, the father is little a, little a. We know that because he's affected. And the only way you can be affected is to have two little a's. So we know one of the little a's came from the father, and we also know the other little a came from the mother, but the mother is unaffected. So she must be genotype big A, little a. This is one of your study guide questions, by the way. Then we look down at the second generation. They had a son who was affected and a daughter who's unaffected. But we know that daughter has a little a because that's all the father had to give. Then we go to the third generation. I am sorry. I completely made it look like that the son and the daughter had children. I'm so sorry. We don't know that this individual that I'm putting an asterisk beside, we don't know that she is big A, little a, except for the fact that she's got a child who has two little a's. We don't know it because this is not her father. This right here, number one, the individual number one is not her father. That was my mistake. So individual 1 and 2 had a son who we know is affected, who we know is little a, little a. And we also know the genotype of his of the woman he had children with is big A, little a, because they had 3 children. They had a child who was affected, so one of the little a's had to have come from the mother. And then they had a son who's unaffected and a daughter who is unaffected. We do not know because the son never had children. This individual that I'm putting the asterisk by, we do not know if he is big A, or big A, little a. There is actually, yes, we do. We do know because his father only had little a's to give. So I don't know if this is a mistake or if they wanted us to figure this out. But he could only get a little a from his father. So he's definitely big A, little a. And then they had a daughter that's big A, little a. She had children with a man who is big A, little a. And we know that both these individuals have little a's because they ended up having a child who was affected with alkaptonuria, a daughter. And if the daughter has two little a's, she got one from her mom and one from her dad. We do not know in the fourth generation, this daughter, we do not know if this daughter is big A, or big A, little a, because she could have gotten two big A's from her parents, or she could have gotten a big A and a little a. But this individual here, that is a mistake in the illustration. Whoever drew it just made a mistake because the father only had little a's to give. Now, looking at individual 3 is unaffected but has a child who is affected. So individual 3 must have genotype big A, little a. And it seemed like there was an individual 4. I guess not. Okay, because I know there's a question in your study guide about this. Now, we're going to look at a dihybrid cross. A monohybrid cross, remember, was when we had parents like this. Big P, little p crossed with big P, little p. They're hybrid. Both of them are hybrid because they have two different alleles for the trait, a big P and a little p. If they were homozygous or not hybrid, they would have had either two big P's or two little p's. Then we would say they were pure. But when we do the cross, we're looking at one trait, and that makes it a monohybrid cross. Now, in the cross below, we are doing a dihybrid cross because we're looking at two traits at the same time. Now, if you look in the table, the P generation is here and here, and you can see that the yellow seed has the genotype big Y, big Y, big R,